Hey everybody, Dr. Vizo here. In this video, we're going to talk about cytokines. And this is one of those chapters where it's really good to use the immunology bites that you'll see on the site. Those will really help you kind of categorizing some of this information. This is one of those areas where you want to use flashcards or something to remember these. But what I'll say overall is if you can classify this information and understand what these cytokines are doing in terms of communication, it makes the mechanisms a lot easier. And so we'll start with the pro-inflammatory cytokines just because we've talked so much now about the acute inflammatory response. It's going to make for an easy transition. And then we'll talk about some additional cytokines, some things that we haven't quite talked about as much yet. Going on to that, we'll talk about pro-inflammatory cytokines, like we said first. And when you're thinking of cytokines, what are we talking about? We're talking about, if you have two cells here, right? You got an antigen presenting cell, you got a naive T cell. Essentially, we're saying, what do these two cells use to communicate? And what they use is cytokines, right? So one cell can release molecules to tell a dendritic cell to do one thing or the other. And you can see different cytokines can cause different types of responses and can cause, this dendritic cell to essentially behave differently. Okay, and so that's what cytokines are doing. They're communicating between cells. Okay, so again, when we categorize this in terms of what these cytokines are doing, I like to start with the acute inflammatory response, just because this is where it all starts. This is what we keep talking about, is this acute inflammatory response. Remember, how does this happen? And again, I'm going to go through this fast because we've talked about this, probably in 3 of these videos already. So go back, check the other videos out if you're not familiar with this. But again, pattern recognition receptors are going to bind to these non-specific pathogen-associated molecular patterns or damage-associated molecular patterns, right? Things like LPS, for example, binding to toll-like receptors, or the damage-associated molecular patterns. Cells that are infected with a virally infected cell, for example, that is releasing its cell contents, those contents binding to these pattern recognition receptors is going to set off a non-specific innate immunity cascade, increasing NF-κB. NF-κB is going to lead to the downstream transcription of interleukin-1, interleukin-6, TNF-alpha, leading to production of acute phase reactants and increases in temperature set point, or we can just say increase in fever, okay? And also an increase in expression of endothelial adhesion molecules, right? We've talked about this in great detail in the last video. What's the point of that? Well, let's say you have an infection somewhere, right? You want neutrophils to get to the site of that infection. You want them to get to the site of inflammation. And to do that, you need to put endothelial adhesion molecules on those endothelial cells. So when the neutrophils come in rolling, they're going to bind really tightly to those endothelial cells and get in through diabetes to the site of infection. And again, we talked about all of that in the last couple of videos, but it's essentially this process that causes that, right? Interleukin-1, interleukin-6, TNF-alpha. So if there's nothing else that you want to remember from this first category, if there's only one thing you can remember, it's definitely going to be this. And you're going to remember neutrophil chemotaxis is largely driven by interleukin-8, LTB4, C5a. And again, we've talked about all of this multiple times in the last few videos. But again, these are the communication pieces that the body is using to, number 1, increase temperature set point, set off an acute inflammatory cascade, and then number 2, allow neutrophils to taxi to the location of an infection. The thing that we haven't talked about as much is going to be the proliferative response. And when you're thinking about the proliferative response, I've got the innate response down, right? We got innate immunity. But what about my immune cells? What about my T cells? What about my B cells? What about my natural killer cells? That's going to be this proliferative response. We want those cells in the party too, right? Because they're ultimately going to help build memory responses, cell-mediated responses, humoral immunity, right? So to do that, the number 1 cytokine you need to remember is interleukin-2. So let's just say that we have some cell here, okay? So we're just going to take an example here. Let's just say that we have a T cell here. Now let's just say that it's a naive T cell. Now you've heard this term before, right? You've seen it here too. What is a naive T cell? Naive essentially means that this T cell has not kind of run into its antigen yet. So if I were to draw a T cell receptor on here, maybe I have a unique structure here, okay? So this cell's T cell receptor, TCR, okay? So this T cell has a T cell receptor, and it's got some other receptors out here too. Let's just say it has another receptor here. This will be its interleukin-2 receptor, and you'll see where I'm going with this in a second. So what will happen is, at some point, this T cell has a very unique T cell receptor, and it might even have some neighbors here, okay? But this T cell has a different T cell receptor, okay? But it does have the same interleukin-2 receptor. So that's kind of its neighbor cell, and then maybe it has another neighbor cell on this side. Another T cell here, again, unique T cell receptor, okay? So there's a T cell receptor, but then it also has that same interleukin-2 receptor. Eventually, what can happen is, let's just say that there is some dendritic cell, okay, or some antigen-presenting cell, and that antigen-presenting cell right? So this is my dendritic cell. Okay, this dendritic cell is going to eventually, maybe it runs into a bacteria or some pathogen, right? And so that dendritic cell is then going to take that pathogen and it's going to display, an antigen, right? A component of that pathogen on this MHC receptor. So let's just say that this is the antigen. Okay, so it's displaying out on this MHC receptor. Now, if this dendritic cell presents the right fit for that antigen to the right fit for that T cell receptor, if these two can bind and lock in, and let's just say that these two are a perfect match, this T cell will then become activated. Okay, so it will go from naive to activated, to that antigen that fits nicely into that T cell receptor. And again, this antigen, if it binds here, it might not fit nicely. It might not fit nicely at this T cell. Okay, it's going to bind to a very unique arrangement of a T cell receptor. Now, what will happen is once this T cell gets activated, it says, okay, hey, look, there's a problem here, right? There's potential pathogen present. And so what this T cell will do is it can start to release interleukin 2. Interleukin 2 is going to allow for increased proliferation of immune cells. T cells will have increased proliferation. B cells will have increased proliferation, natural killer cells as well. Now, it does this in a few ways. One of the classic things that sometimes gets asked about for interleukin 2 is that it has autocrine action. Now, let's just talk about that for a second. Let's start with something that we already know. Okay, let's just say way off, let's just say away from these cells here, there's a lymph node. Okay, there's a lymph node. And inside that lymph node, maybe we have another T cell. Okay, maybe we have another T cell inside of this lymph node. I'm going to put LN down here for lymph node. And to get into that lymph node, maybe there's an afferent arteriole over here. Okay, so you got to get into the bloodstream to get into that lymph node. Now, maybe this interleukin 2 can travel through the bloodstream, right? It can travel through the bloodstream all the way to this lymph node to eventually bind to this T cell's interleukin 2 receptor. That would be an example of endocrine action. Okay, and so that's what we talk about when we talk about the endocrine system. We're talking about hormones that are traveling in the blood to get to a distant site. That's what endocrine is. If we talk about paracrine action, okay, so paracrine would be if this interleukin 2 that this activated T cell released, maybe it bound to this interleukin 2 receptor, or maybe it bound to the interleukin 2 receptor over here at the neighboring cells, the cells around this T cell. That would be an example of paracrine action. Okay, so that's paracrine. Now, if this interleukin 2 went and maybe it bound to the same cell that released it, okay? So in other words, this activated T cell is releasing interleukin 2 that is then binding to the cell that released it. That would be an example of autocrine action, okay? So I know that can be a little confusing, but the classic thing to remember when you think about autocrine action is interleukin 2 is the one that usually is going to get asked about in relation to autocrine action. Now, interleukin 3, okay, remember in the very beginning, the series when we talked about, okay, this is kind of the lymphoid lineage, your myeloid lineage. When you're thinking about interleukin 3 in general, just high level, you're usually talking more about, stimulating the bone marrow to release some of those cell lines that we're going to talk more about in hematology. Okay, so I think of interleukin 2 more in immunology. I think about interleukin 3 more in hematology. Okay, so we'll make more distinction on that as we go into hemonc. But that's kind of my way of thinking about it. It's going to increase hematopoiesis. This is your acute inflammatory response, more of the innate response, proliferative response. Now we're starting to ramp up into a specific T helper response, which we'll go into next. So let's just start touching a little bit on this T helper 1 response. And we actually talked about this quite a bit when we talked about things like granulomas. The T helper 1 response is going to be very closely linked to a cell-mediated immune response. And we're going to talk about this in great detail when we talk about the T cells. But in general, you want to think about kind of your end game here is CD8 positive T cells and natural killer cells. Okay, so that's where this is kind of headed, okay, this whole process, and you'll see what I mean. So let's just say, if we wanted to just explain this a little bit, let's just say that we have some antigen presenting cell here, okay? Let's just say that it's a macrophage. I'm just going to write MO here for macrophage, and it's going to have interacted with some pathogen. It's going to present that pathogen on an MHC receptor. Now remember, there's two types of MHC. There's going to be MHC1 and MHC2. Remember, MHC1 is going to bind to CD8 positive T cells. Remember your rule of 8s. 1 times 8 is 8. So MHC1 binds to CD8 positive T cells. But for the sake of this example, we're going to say this is MHC2, which means that the antigen on here is going to bind to a CD4 positive T cell. Okay, so here's my antigen. Okay, and so there's my macrophage. So it's interacted, maybe it phagocytosed some bacteria, for example, and now it's presenting that component, that antigen, to a T cell. Okay, and let's just say that over here I have my T cell. Okay, so I have my T cell, it's CD4 positive, and it's naive. It hasn't interacted with an antigen that meets the criteria for this antigen receptor. Okay, so let's just say that this T cell receptor fits nicely with this antigen, right? And let's just say that this antigen binds to this T cell receptor. Okay, so in that case, if these were to bind, this T cell, like we just said, would then become activated. Okay, so then this T cell would be activated. It would no longer be naive. Okay, so we'll cross out naive, now it's activated. Now after this binding happens and this starts to get activated, the macrophage is going to release some cytokines, okay, some cytokines over to the T cell. In particular, we're going to release interleukin 12, okay, and that's what you can see here. So once this macrophage presents the antigen to this T cell, it's going to release interleukin 12. Okay, and that interleukin 12 is going to help stimulate this T cell to become a T helper 1 cell. Okay, a T helper 1 cell, which is going to take us into this T helper 1 response. Now you have a T helper 1 cell, and it's going to say, hey, right back at you, macrophage. It's going to send interferon gamma going the other way. Okay, so now this T cell is going to send interferon gamma back to the macrophage. Okay, and we'll talk about what this is in just a second. Okay, so the interferon gamma is going to stimulate the macrophage and activate the macrophage. Okay, so you're going to get some macrophage activation too from this interferon gamma. You know what, I'll do this in pink just to keep my colors consistent here. Okay, so this macrophage is going to get activated now because we sent some interferon gamma its way. Okay, I'm going to put an A here for activated. And it can also send some of this interferon gamma to the CD8 positive T cells. I always think of them as the scary cytotoxic T cells. Okay, so these are the really scary, mean cytotoxic T cells. We're going to CD8 positive T cells. And it's going to send some interferon gamma to them too. And that's also going to activate these CD8 positive T cells as well. And so that's essentially what's happening. So just to recap this really quickly, the macrophage had an antigen that was bound to its MHC2 protein that fit to this T cell receptor on this specific T cell, and then that macrophage released interleukin 12 to turn this T cell into a T helper 1 cell. This T helper 1 cell then released interferon gamma back to the macrophage, activated the macrophage, and also some of this interferon gamma could potentially reach some of these cytotoxic CD8 positive T cells to also look for this pathogen. Okay, so that's this whole process. And remember, there's also other things happening. You might say, like what? The other thing happening is interleukin 2, right? We already talked about interleukin 2 can also be released as a general proliferative response for all immune cells. It's not as specific to T helper 1 or T helper 2 response. Okay, but this is the process for the T helper 1 response. And where did you see this response already? Well, you saw this response when we talked about granulomas. It's very classic to see this T helper 1 cell-mediated response for granulomas because you have all these macrophages getting activated, turning into epithelioid cells, and then eventually giant cells. Okay, and you have all this interleukin 12 that's essentially sustaining this granuloma. And you can kind of see that up here. So if you look, interleukin 12, right, being released from the dendritic cell to the naive T cell. Remember, these are our communication lines. This interleukin 12 can then cause your T cell, your naive T cell, to form a T helper 1 cell that then releases interferon gamma. So that's the T helper 1 response. If you got that down, if you know where these factors fit, right, you can make sense of a lot of these different processes. It's not as complicated as it looks. And again, it's the same thing here. You have the antigen presenting cell binding to a naive CD4 positive T cell, MHC2 binding to the T cell receptor. Okay, we'll talk about this in a future video, but essentially what's happening here is this connection is causing lines of communication to be sent from one cell to the other, right? Interleukin 12 and then interferon gamma going back the other way. Okay, that's what these polarizing cytokines are. They're very specific for the T helper 1 response. Now, the last thing I want to touch on here is going to be interferon alpha and beta. Interferon alpha and beta, think of them as kind of in this separate class from interferon gamma. These are going to be particularly important for managing viral infections. So the big thing that these two cytokines are going to do is they're going to allow for there to be an increased expression of MHC1. Now remember, MHC1 is on almost all of our cells. Okay, so cells that have nuclei are very classically going to have MHC1 on them. So it doesn't have to be an immune cell. It doesn't have to be a phagocyte or an antigen presenting cell. It can be almost any cell that has MHC1. And the whole point of that is, if there's something wrong with one of our cells that's not involved in the immune system, it will then potentially be presented on the MHC1 to mark that cell, to say, hey, there's something wrong with that cell. Let's destroy it now before a potential virus or cancer in that cell replicates, right, and then affects the cells around it or metastasizes. Okay, so that's the whole point of MHC1. It's a marker for each cell. Okay, so if you have all of your cells, right, you have essentially a receptor on there, and if there is something wrong, right, if a virus gets in, let's just say we have a virus here. Okay, we have some virus here. If this virus infects this cell, then this marker on the cell is going to tell us, hey, this virus infected this cell. And that marker, again, is MHC1. It's on all of these cells. Once we find out that there's something wrong with this MHC marker, then these CD8 positive T cells, remember, they are the ones that are binding to MHC1. They are going to go after that cell to destroy it before that virus can hijack the cell machinery and then affect all of the cells around it. Okay, so that's the point of MHC1 simply. And interferon alpha and interferon beta are the cytokines that are essentially upregulating the MHC1 exposure here. So they're putting more MHC1 receptors so that there's a higher likelihood that these cells will then present these viral antigens, right, so that they can more quickly be destroyed if infected. That's the point of interferon alpha and beta. So if there's a viral infection present, interferon alpha and interferon beta might be upregulated, especially locally here, to tell these cells, hey, upregulate your MHC1 receptors. There's a high risk of a virus around us, potentially. Okay, and so that's what they're doing. And also they have some other effects. They can also break down mRNA so that a virus that does infect a nearby cell can't hijack gene encoding processes to allow for viral replication. Okay, but that's the key here. Interferon alpha, interferon beta classically going to be used to kind of protect from viral infections. Again, interferon gamma in a whole different spectrum. Interferon gamma, we're talking mostly about things like T helper 1 response, granulomas, activation of macrophages. Now, when we go into the different deficiencies and diseases, if you just understand this process, you can make complete sense of this. For example, if you have a patient that has interleukin 12 receptor deficiency, okay, so the receptor that binds to interleukin 12 here, let's just say that it's not there for whatever reason. If you don't have interleukin 12 receptors, right, then when the macrophage tries to activate the T cell to make T helper 1 cells, it's not going to work because the CD4 positive T cell doesn't have a receptor for it. So to get around that, you can give the patients interferon gamma. You can bypass that step and just give the patient interferon gamma, and that will continue to protect patients from things like TB. If the patient did not receive interferon gamma, right, and they have an interleukin 12 receptor deficiency, right, you're never going to be able to have a good T helper 1 response. And so these patients will have higher risk for conditions that can predispose them to things like granulomas, right, which are maintained by interleukin 12, specifically mycobacteria, tuberculosis specifically being the big one. Okay, so that's just how you got to think about it. Conversely, if you have a patient that has an interferon gamma receptor deficiency, if you give them interferon gamma, it's not going to help the situation because the macrophages can still not get activated because they don't have the receptor. So in a situation like that, you might just want to treat the underlying infection. For example, if a patient has TB and they have interferon gamma receptor deficiency, you would just treat them more aggressively for TB using RIPE therapy, etc. Okay, so again, just making this big picture, that's how you think through these mechanisms.